The invention of the Fourier tool, especially the Fourier series, is one of the crowning achievement in the 20th century. And since this particular mathematical tool has been invented, of course, by the scientist Jean Baptiste Fourier, the applications of this particular Fourier series have been reached to a far level in the various fields of the science and technology here. Now, as far as the Fourier series development is concerned, we find the Fourier series is having a strong connection with the geometry here. So, let us understand the theory of the Fourier series from a geometrical point of view. Now, if we look at the Fourier series, we have a notice that it has a familiarity with the vector algebra and the coordinate geometry, and the strong analogy between what we do in the signal processing and what we do in the vector algebra will be very much helpful to proceed further in this particular chapter to complete the wavelet transform theory understanding here. So here we are having one aim, that is to relate the geometry with the Fourier series here. Now, Fourier series, the formulation, I hope you understand. The signal represented in its particular coefficient form or the basis, functional basis, I must say here. We will come to that particular formula, but we will have a focus on the first type here, that it is geometry. Then we shall relate it to the Fourier series here. So as far as the geometry is concerned, we should have a background or just a recap of what we know from the vector algebra here. See, vector, the term, I hope it is very clear to people that it is different than the scalars. In our day-to-day life, we are dealing with various quantities here. So those quantities we can distinguish as the scalar quantities and then the vector quantities. So first of all, what are the scalar quantities? The quantities whose value may be represented by a single real number. So the quantities which possesses only the magnitude, we call them as the scalar quantities. The examples we can list out as the distance, then the temperature, mass, density, pressure, volume, voltage. So all these particular quantities are there having magnitude only, and with the help of the SI system of unit, we represent that particular magnitude for the concerned quantity here. Now, when it comes the question of the second type, that it is vector quantities, we can describe the vector quantity anyone, a quantity that has both the magnitude and direction into a space. See here, the word in space is very important here. Now, the consideration of the space can be of the various types here. It can be of a two-dimensional space or a three-dimensional space, etc. here. Now, for example, we can have the quantities as like the force, then the velocity, then the acceleration here. Now, mostly in our real world, we have to deal with the vector quantities. That means we have to simultaneously deal with the magnitude as well as the direction here. See, dealing with magnitude is sometimes convenient as compared to dealing with the direction here, because the direction brings the complexity into the analysis here. So for the vector quantities, we perform various kind of the operations. Those we can mathematically write in the symbolic forms. We have the simple operations as like the vector addition. As far as the geometry is concerned, see here, any two vectors when are added for the vector addition here, see, this is just the representation of vector A. So capital letter is used here and an arrow is shown here. So the arrowhead is showing us the direction of that particular quantity. So this is the vector A, this is the another vector B here, and the addition of the two, here it is performed by the parallelogram law of addition here, and we find another resultant vector which you can name as vector C as well, that is equal to A plus B here. Now this was the parallelogram law of vector addition. We have also another alternative, that is triangle law of vector addition. The second vector is a match as such that its starting point is at the ending point of the first vector. Then the arrow or the vector drawn from the starting point of the first vector to the ending point of the second vector will be just the vector addition. So here it is represented a plus b. Similarly, we have the vector subtraction as just reversing the direction of the second vector and just following the vector addition, we will get the vector subtraction here. So a minus b can be performed if we have a plus minus of b here. So these are the vector operations. Simply we have done with the vector addition, subtraction. Similarly, we have vector multiplication also. Now, while dealing with the vector quantities here, the positioning and locationing of the vectors is very essential, and for that purpose in the vector algebra we have a study of coordinate systems. Now basically we have the three most useful coordinate systems into the syllabus of science and engineering. These are the rectangular coordinate system, the cylindrical coordinate system, and the spherical coordinate system here. Now let us have few of the illustrations which will help us to have differentiation between these coordinate systems, and then finally we will relate them to the topic Fourier series. So let us have the first type, the rectangular coordinate system. See, in this particular coordinate system we have the three references as the three axes which are mutually perpendicular to each other. See, this is what the capital X axis, this is what the capital Y axis, and this is what the capital Z axis. Now you see Z axis is having the upright orientation. It is going upwards for the positive values, downwards for the negative values, as we can draw in the reverse direction. Similarly, in the plane of the digital screen that you are watching, on the right hand side we have the positive values of the Y. In the negative side, that it means on the left hand side, we can have the negative values of the Y, and a perpendicular direction to this digital screen that is coming outwards to you and inwards in the reverse direction. So this is what the X axis here. Now any vector that is joining the origin, which is the intersection of the three axes x, y, z, to a point here, that is a vector r here. Right now we are concerning about only the magnitude here. See, when we drop a perpendicular from this particular point on the xy plane, have intersection with the x and y axis, drawing these particular lines, we get the measurements of x and y here. And similarly, having a perpendicular on the z axis, it will also mark the z unit here. So this is what the magnitude in x, y, z, so that the addition comes out to be equal to r here. So how much the point is far in the direction of x, in the direction of y, in the direction of z, addition of the three will be equal to r here. So this is what the concern with respect to the magnitude only. When we need the requirement of representing the direction here we make the use of the three unit vectors as denoted ax, ay, and az. So using these references, capital X, Y, Z axis and the unit vectors, we can denote any vector joining a point with respect to a reference position of the origin here. We can express that particular vector as, suppose for example we have capital A, we have ax into ax, ay into ay, az into az, all the three are added to each other. So in the small casing we have the unit vectors giving the directional information here, whereas capital AX, capital AY and capital AZ are these magnitudes that particular point has traced while going away from the origin here. Now you see here, for representation of this information we have taken the use of these reference axes XYZ and the unit vectors. So there it is a question, while having a representation of the signal with any of the mathematical tools as like the Fourier series, what are the basis, what are the references with which we are going to have that representation completed. So this was the thing that we have compared the representation of a signal with the help of the mathematical tool as like for example Fourier series with that of the representation of a point into a three-dimensional space by using this rectangular coordinate system. Similarly, we have the another alternative, that it is cylindrical coordinate system. In the cylindrical coordinate system discussion, here we are going to make one thing, that point is the same but way of representation is different here. Now if you recall back from the vector algebra, see this is the point. Now with respect to this particular point, we are having the reference as considered in the cylindrical coordinate system, that it is z-axis only. So we imagine a cylindrical surface as shown in part here, that is centered along the z-axis. So the point is considered to be on the surface of the cylinder. So if we join that particular point to the z-axis, it means dropping a perpendicular onto the z-axis, that distance it will be a radius of the cylinder. So this is one parameter rho, radius of the cylindrical surface. Now if we have this particular radius at a given point like this here, and if we have the imagination of the positive x direction, the angle between them is denoted by the phi here in this particular direction. This is the direction of measurement of angle phi with respect to the positive x direction here. And next to that, how much is the height of the point P with respect to the position of the origin? If this is the z-axis, this is the x-axis, and this is what the y-axis, the intersection of the three is origin. So if it is upwards, the z value is positive. If it is downwards to origin, z value is negative. So rho, phi and z are the three parameters to have representation of the same point P that we have done into the rectangular coordinate system. Now these are the corresponding unit vectors directed in the progression of that particular parameter rho, the radius of the cylindrical surface, a phi and then a z here. So by using these references and the corresponding unit vectors here, in general for any vector A joining a certain point with respect to the origin here, we have the representation using cylindrical coordinate system like this. So a rho added by a phi added by az here. So here the rho, phi and z, these are the functional basis, you can say, if you are talking about signal information, or simply the references. So again, the question to your mind, in the Fourier series, what are the references with respect to which we can have the representation of the signal and its components? So we have to relate the Fourier series geometrical point of view. So this was the discussion with respect to the cylindrical coordinate system. Now let us talk about the rectangular coordinate system. In the rectangular coordinate system, we have again the same point P here, but in the consideration of the spherical coordinate system, this is just joined to the position of the origin, the intersection of the three axes x, y, z, and this much of length as denoted by r is considered to be radius of a sphere. A sphere has to be imagined that is centered at the origin here, and the point P in the space is considered to be on the surface of the sphere here. Now this is one parameter, that is r, radius of the sphere. If this particular radius segment is making certain angle theta with the positive z direction, this is another angular parameter theta, and the phi definition as discussed in the cylindrical case remains the same here. So r theta phi defines the three spherical coordinates. Now along with we have the three unit vectors as denoted. We have ar, a phi, a theta. So by the use of these reference parameters r, theta, phi and the corresponding unit vectors here, we can have the representation of any vector using the spherical coordinate system. So just coming back to the Fourier series. So in the Fourier series, the most general formulation for representation of any signal f of x which is periodic in nature is given by this mathematical expression. Now you see, generally we are having the signal one dimensional signal graphically represented like this. So we have the quantity f with respect to the quantity x here. So x is the independent parameter depending on which the f has the values here. So it may be a sine function, it may be a cosine function, or any function here. Here for Fourier series especially, the f of x is of periodic nature. The same pattern is going to repeat after a specific interval of time here. Now by the use of Fourier series, this is expressed as shown in the RHS. So in the RHS we can have the three terms. The first term is having a0 divided by 2. The second term is having the summation of an into cos nx for the index variable n is equal to 1 to infinity, whereas in the third term we have again the summation for index variable n is equal to 1 to infinity for the multiplication of bn with that of sine of nx here. So of course we have the cosine component here, sine component here. Just focus on a0, an, bn and the rest of the details. We have to check what are the references into the three-dimensional or two-dimensional or the functional space in general, you can say, based on to which we can have the representation of the original information, that is our signal of interest here. So if we have a clear understanding of the Fourier series with respect to the geometrical point of view, so it will have a solid foundation to switch from Fourier theory to that of the wavelet theory here.